we can use definite integrals to find areas of planar regions. So if we consider this region R, and this blue function as f of x, and the other function as g of x, and we break this region up into infinitely thin rectangles which have a width of dx, then the height of each rectangle is f of x minus g of x. And we multiply this by dx, which gives us the area of that rectangle, and then we integrate from x equals a to x equals b. And that gives us the area of the region. Let's find the area of the region bounded by the curves y equals x squared and y equals x to 1/2 over the interval from 0 to 1. And we're asked to use rectangles that are perpendicular to the x-axis. So therefore the thickness of the rectangle is dx, and to obtain the height, the square root curve lies above the parabolic curve. So what we do is subtract x squared from x to 1/2 to get the height of that rectangle. And then summing up the areas of the rectangle from x equals 0 to 1 is effectively what this integral is doing. And that gives us the area of this entire region. And you can easily evaluate this integral. We can also use definite integrals to find the area between curves using functions of y. So suppose this curve is y equals f of x, and this is another one with y equals g of x. And we choose rectangles parallel to the horizontal axes, which have an infinitesimal thickness dy. So to integrate with respect to y, we need to write x in terms of y. So what you do is solve for x, and you'll get x in terms of y. So for example, u of y, and here you'd get x is equal to v of y. And therefore the width of this rectangle is v of y minus u of y, and then multiplying by dy gives the area of that infinitesimally thin rectangle. And then integrating from y equals a to b is effectively summing up the areas of those infinitesimally thin rectangles from a to b. And that gives us the area of this region. Let's find the area of the region bounded by the curves y equals x squared and y equals root x over the interval from 0 to 1. And we're asked to use rectangles that are parallel to the x-axis. So these are horizontal rectangles that are going to have an infinitesimal thickness dy. And to obtain the length of that rectangle, we need to write these equations for these curves in terms of y, because we're going to integrate over y. So x is effectively equal to y squared, and for this case, x is equal to y to the 1/2. And the parabolic curve lies to the right of the square root curve, so we use y to the 1/2, and then subtract y squared to obtain the length of that rectangle. And multiplying by dy gives the area of that rectangle, and we integrate from y equals 0 to y equals 1. So this basically sums up the areas of those infinitesimally thin rectangles to give the area of the region. And you can easily evaluate this integral and compare your result where we use the vertical rectangles instead. We can also use definite integrals to find the areas of planar regions that are bounded by several curves, and the curves intersect. So in this case, to find the area of both of these regions, we can use a piecewise integral, and if we designate this function f of x and this one as g of x, and the thickness of each rectangle dx. Then the area of the first region is f of x minus g of x, which is the height of one rectangle, and then multiplying by dx gives us the area of that rectangle. And then we integrate from x equals a to x equals b, and that gives us the area of that first region. And similarly for that second region, we integrate from b to c, but this time the height of each rectangle is g of x minus f of x, to give us a positive height for that rectangle, which we integrate with respect to x. And that gives us the area of the second region. And sometimes you have to use some algebra to find the coordinates of that intersection point. Let's find the area of the region bounded by the parabolic curve and the square root curve over the interval from 0 to 2. And we're asked to use rectangles perpendicular to the horizontal axes. So these are going to be vertical rectangles with an infinitesimal thickness dx. So from the interval from 0 to 1, the square root curve lies above the parabolic curve. So we subtract x squared from x to the 1/2 to obtain the height of that rectangle, and we integrate from x equals 0 to x equals 1. Now for the interval from 1 to 2, the parabolic curve lies above the square root curve, so we subtract x to the 1/2 from x squared to get the height of that rectangle, and then multiply by the infinitesimal thickness dx, and integrate from 1 to 2 to obtain the area of that second region. And evaluate these integrals and post your answer in the comments.